Okay, great. So here are some structural properties that isomorphic graphs must share. Obviously, the number of vertices. If two graphs had different numbers of vertices, you wouldn't even be able to make a bijection, let alone make the edges be preserved, right? So number of vertices. The second one, which is the second most obvious thing, would be the number of edges. Right? So both graphs would have to share the number of edges as well. The number of edges is related to the degrees of the vertices. So we talked last time about something called the degree sequence. So two graphs that are isomorphic would have to share the same degree sequence. So these are just some examples of structural properties that two isomorphic graphs would have to share. So not only would the degree sequences have to be the same, but the relationships between the vertices of certain degrees would have to be consistent. Let's say that both graphs have two vertices of degree 7. And in the first graph, those two vertices are adjacent to each other. Well, then in the second graph, they would have to be adjacent to each other. So everything would have to be totally compatible that way. So relationships, this is kind of a more vague statement, but just to give you the idea. Relationships between vertices of various degrees. So something like that would work. On Thursday last week, we also talked about taking walks in a graph, and a graph would be connected if you can walk between any two vertices with a sequence of edges that goes through that graph. So connectedness is another good example. If one graph is connected and another one isn't, well, then they're not going to be isomorphic, right? They would for sure be not isomorphic in that case. Let's see, I'll write down another one here. What about existence of cycles of various lengths? So again, a cycle is just really, it's a closed path. Sorry, I'm just going to try to log on to my Canvas here real quick so that I can just get this. Can't get this group work off my mind. Somehow I don't seem to have it here, so I'm just going to pull up this thing here. And then, sometime in my lifetime, this projector might come on. And then if that happens, we'll be able to put them up on the, oh, there we go. So the graphs can come up on the screen here. Let me try to just download this real fast. Sorry, guys. Open this up. And there we go. Don't need that. So this will be helpful for us. We'll have some examples that we can look at in just a second. I have one more thing here to list, though, in my list so far. Number 7 is planar. So I didn't put this in the recap either, but if two graphs are isomorphic, then if one of them is planar, the other one has to be planar. And if one of them is not planar, then the other one should be not planar, right? So they have to be compatible in that respect. The main thing I want to say here, though, guys, is that this is actually ... This list has no end. As many different graph theoretic principles as you can come up with would be things you could add to this list. Okay, and these are just a few of the things we've kind of gotten into so far, but it's certainly not meant to be an exhaustive list. So what I want to say here then is to disprove that two graphs are isomorphic. To disprove that two graphs are isomorphic, right? We just need to find one structural difference. One structural incompatibility, or I'll just say difference. Could be anything. I usually go down the list somewhat in this order. I first check how many vertices I have. I count the edges. I look at the degree sequence, then I look for relationships. I kind of just go in order, but you can do any order that you want, and this is how you disprove the two graphs are isomorphic. Okay, so these are the yes, no question, right? As you can see, I give you two graphs at a time. I just ask you, are they isomorphic or not? Okay. And then I'll put another little bullet point here to address the opposite scenario, which is to prove that two graphs are isomorphic. If they are isomorphic and I want to prove it, to prove that two graphs are isomorphic, we must find, or we must exhibit this theta, this function theta that I referenced in my recap over here, in order to do that. So again, coming back to the recap, I started the Zoom a little bit late, but there will be a bijection theta between the vertices that preserves edges, right? So we would have to exhibit that. Now, I will normally be okay with you just writing down what theta is. Technically, just telling me what theta does to the vertices isn't the only thing you need to do, because you would also need to verify that the edges are preserved. But you could imagine how many potential edges and non-edges you have in a graph. It would take a long time to do that. So I usually don't ask for that. I'll just ask you to give me the function that the bijection between the vertices, and then but I may check your theta for you and make sure that it really does work. So you should do that. You shouldn't just write down a random bijection and assume it's going to work. Usually that won't be the case. Yeah, that usually won't be the case. Okay, so let's do a couple examples together, and then I think I'm going to try to do this group work without the group work handout. We'll just see if we can make the most of the handout that I've put up on the screen there, projected onto the screen. Are there questions though so far? Just kind of getting us back where we left off last Thursday. So let's just do this example. Are these isomorphic? Okay, so we'll do a couple of examples. Here's the first one. So for my first example, I'm going to make a square, four vertices into a square, and I'll put one vertex in the center of this thing. So we'll connect up the outside of the square, like so, and then I'm going to go diagonally down from the upper left to the lower right, passing through that center point, and I'm also going to make an edge that goes from the center point to the lower left corner of the graph. So that's my first one. And then for my second graph, I'm actually going to arrange the vertices like they look like they're from a pentagon. And I'm just going to connect the edges of this pentagon on the outside. And then I'm going to pick the vertex over here on the right and connect it up to all of the other vertices. So I'll just do this picture here. Okay, so here are my two graphs for our first example, and the question is, are they isomorphic or not? Does anybody have a suggestion what I might want to do first? Jose?
Label.
Exactly. If you want to start talking about the vertices here and making this bijection, you need to label the graph. I like to use, if they haven't done it for me already, then I can label it however I want. I like to use letters on one of the graphs. So maybe A, B, C, D, and E would be a good choice on the first graph. And then on the second graph, I probably would choose numbers instead, just so I don't have any chance of getting confused between the inputs and the outputs. So we should label our graph accordingly with some labels on the vertices like that. Okay, and then you're not normally just going to look at the graphs and immediately be able to tell me whether they're isomorphic or not. Some of these can be pretty tough, actually. These can be pretty tough. So what I like to do before I decide yes or no on the isomorphism is I like to sort of go through at least the first part of my list. If I can get through a good chunk of these items, right, and have compatibility all the way along, I'm gonna start to feel pretty confident that if most of these properties are being preserved, there probably is going to be an isomorphism. Okay, so let's just check this out. And so this first graph, by the way, I'm gonna call it G with vertex set B and E. And then the second one, I'll call it G prime with vertex set B prime and E prime. So I like to have those labeled. And let's just check the number of vertices. Is that compatible between the two graphs?
Yes.
Definitely, right? There's 5 vertices in both graphs. So that's for sure compatible. What about the number of edges?
Yeah, they're both 7.
Number of edges. By the way, sometimes it's hard to count the edges directly. If that happens, what's another way that you can count the edges?
What is that for?
Some of the degree sequence.
Exactly, the handshaking theorem, right?
Yeah.
If I add up the degrees of all the vertices and then divide by 2. So if you add up the degrees of these vertices on this graph, 3 plus 2 plus 3 plus 3 plus 3 is 14, I think. And so you divide that by 2, you get 7. So the first graph has 7 edges. And if you add up the degree sequence of the second graph, I have 2 plus 4 plus 2 plus 3 plus 3. I think that's also 14. So these seem to be agreeing. Oops, that's E prime. They seem to be agreeing on the number of edges. So the graphs have the same vertices, the same edges. What about the degree sequences? That's, by the way, I'm just going in this order. You don't have to go in the same order. Let's see, for the first graph, what's the degree sequence over here? Remember, we always write them down from largest to smallest. So I have 4 vertices of degree 3. So 3, 3, 3, 3, and 2 for this graph on the left, right? But then on the graph on the right, the degree sequence would be 4, 3, 3, 2, and 2. Right? So that's not the same. So you could say the graphs have different degree sequences. So even though they agreed up until now about everything else, the conclusion will ultimately be no, these are not isomorphic graphs because they have different degree sequences. Does that make sense? Kind of how to play the game with that? Okay, let's do one more together and then I'll turn you guys loose on practicing this a little bit for yourself. So I've got a couple more pictures to show you. Let's do number 2. I think I'll have to write this one down over here. And let's take a look at it. So come over here. The second example, I'm going to draw them both in exactly the same shape, which is going to be kind of an elongated hexagon. And so for the first graph, I'm going to connect all the way around the hexagon. And then I'm going to make a cross through the center of it, like that. And then on the second graph, I'm going to draw it so it looks like the same exact configuration. So the vertices are going to kind of be shaped in an elongated hexagon. I'm going to connect up the hexagon again. And I'm going to, this time, instead of doing a crisscross through the middle, I'm going to make it go straight through the middle. By the way, on both of the graphs that I gave you on the first example, there were no crossing edges. And so we would have agreed that both graphs were planar, right? Would that be an issue here?
Yeah. Oh, no, yeah,
No.
they're both not. They're both.
So I've actually represented, well, I've represented this graph with a crossing in it. But would I have to draw it that way?
No.
No, see, I could take this edge out. I'm not gonna do this right now, but just so you can see. I can take this edge out and this is actually planar. So don't get confused. I've taught this class about 7 or 8 times. And so I know that like when I draw something like this, people are like, oh, well, that's not planar. What you mean is it's not a planar representation. But this can be redrawn without crossing edges, so it is planar, even though there is a crossing in the way I've drawn it. So this is both of these graphs are also planar, okay? And again, let's go through and label our vertices. So maybe I'll go A, B, C, D, E, F around the outside of the first graph. And then on the second graph, I'll just do 1, 2, 3, 4, 5, 6, like so. And I'll just try to quickly breeze through the easy stuff here. As you can see, both graphs have 6 vertices, so that's not going to help me. In terms of the edges, I believe both graphs have 8 edges. So they are compatible that way. Technically, you don't need to show the work on this, and you don't have to write all of this down, because if the graphs are isomorphic, this won't be sufficient. And if the graphs are not isomorphic, the only thing I need you to show me is what's incompatible between them. So in some sense, this is not necessary to write all this down, but it's good for our, just train of thought, how we're thinking about this to do that. Let's look at the degree sequences, because that's what got us in trouble on the first example. Over here, I have, well, I think it's 4 vertices of degree 3 and 2 vertices of degree 2. So if I draw out the degree sequence, wouldn't it be 3, 3, 3, 3, 2, and 2? And those degrees do add up to 16, which is double the number of edges. So that seems to be right. What about over here? What's the degree sequence of this graph? I think I heard somebody say it. It's exactly the same. I would agree. 3, 3, 3, 3, 2, 2. Yeah, so they have the same degree sequence. Let's see, what else are we supposed to look at here? Relationships between vertices of various degrees. So that would be things like the 2 vertices of degree 2 in this graph are not adjacent to each other. And over here, they're also not adjacent to each other. You could actually refine that and say something like the shortest walk between the 2 vertices of degree 2 is a walk of length 3 in this graph. Oh, but in this graph, same thing. The shortest walk between the 2 vertices of degree 2 is length 3. Okay. What else could you maybe play with? The degree 4 vertices are all kind of configured here. Sorry, the degree 3 vertices are all kind of configured into a square here. So would that be a problem with this? Actually, you can just do the bow tie.
Yeah, you can do the bow tie, which is like.
Yeah, and that's just the same thing as a square. It's just been twisted. That's all. Remember, this is not actually a vertex right here. So these graphs have been fairly compatible. They're both planar. They're both connected. What about existence of cycles of various lengths? A 3 cycle is just a cycle of length 3 would just look like a triangle. A cycle of length 4 would look kind of like a square or a rectangle. Do these graphs have that? This one clearly has triangles and squares. What about this one? I can make a little square like this, A, B, E, F.
Yeah.
Right? Can you make a triangle? I don't think so.
No.
I don't think so. You can try, like, you'd have to play with it for a minute, but you can try different things. As soon as you draw one edge, if you're making a triangle, you have to find another vertex that's connected to both of those 2 vertices that were on that edge. So like if I chose BE as an edge, now I have to find another vertex that's connected to both of them. And I don't see one. Not one that's connected to both of them.
Yeah.
Right, so that edge wouldn't work. Well, you could try a different edge, you could play around with it. I bet within less than 2 minutes, maybe even less than 1 minute, you would convince yourself there's no 3 cycles here. So the point being that they are not isomorphic. This graph has no 3 cycles. could just say something like that. You know, I would believe you, I think that you looked at it and done due diligence on it. This one does have 3 cycles, all you'd have to do is show me one of them. So I could do 1, goes to 2, goes to 6, goes back to 1, something like that would certainly work. Right, so there's another answer of no, okay? So these 2 things together means that these 2 graphs are not isomorphic. Okay? Clear enough? Questions so far? Let me show you one more, and then I'll feel pretty good that we've played with this enough. So this next one is 2 more graphs. This is number 3. Practice one more time here, guys. So the first graph is gonna have 4 vertices kind of in a row here at the top, and then another sequence of 4 vertices on a bottom row like this. And the way I'm gonna connect things up is, starting in the top left, I'm going to connect up the top left vertex to the 3 vertices on the second row that are below it to the left side. And then the top left vertex, let me just label the vertices first. So A, B, C, D, and then E, F, G, H, like this. That way I can talk about the vertices easier. So B, vertex B is gonna connect to H, G, and E. And then C is gonna connect to H, F, and E. And then D is gonna connect to G, F, and E. So there's the first graph, like so. Right? And my second graph is going to be drawn as a square, and then a larger square kind of outside of it. And the way this one is gonna look is the inside square is all connected up, the outside square is all connected up. I need to turn this. And then I'm gonna draw the diagonal edges up like this. Okay, and I need to put numbers on these corners. So on the outside square, I'm gonna start off in the upper left corner and do 1, 2, 3, and 4. And then I go around on the inside with 5, 6, 7, and 8. Okay. Both graphs have 8 vertices. Both graphs have, every vertex has degree 3. And so that actually means both graphs have 12 edges. Check that out. So there's 12 edges. So again, I guess I'll write it down, although again, this is kind of optional. The number of vertices is 8 in both graphs. The number of edges is 12 in both graphs. Both graphs have the degree sequence 3, 3, 3, 3, 3, 3, 3, 3. Every vertex has degree 3. Both graphs are connected. Planar, I don't know. This one's obviously planar. It's been represented as being planar. This one would take some work to untangle all of the crossings that you see here. But you might well be able to do it, actually. The way I would probably try to redraw this without any crossings is I would take the 4 vertices on the top and I would maybe move 2 of them down underneath. See what I mean? So I could leave the H, G, F, E like this, and I could just leave A and B up here. Right? So you'd still have, you know, those edges and then these edges. Oh, there's still some crossings there.
Yeah.
But then here's C and D, and I could put the C and D down here and try and do the same kind of thing. So C goes to E, F, and H. And D goes to E, F, and G. So I've definitely reduced the number of crossings substantially. But the question would be, could I do any better than that, I might have to try to squeeze the D inside here somewhere and like. I could get rid of even more of those crossings, but this is a little bit unclear. I would just say it's a little unclear at this moment whether that would actually work or not. So we could try. Actually, if the graphs are isomorphic, then I would have to be able to do it. So that there are no crossings. Was it?
Yeah, so I've noticed that sometimes we get a lot of, we sequence of a lot of the same term.
Yeah.
And we express that in like a multi-set.
Oh, instead of writing out all the numbers, actually, no, I usually find that it's best to just write this all out, and I don't see it typically done with any other shortcuts. Good question, but I think. These graphs won't have that many vertices normally, that it would be too much of a burden, so this would be as good as anything. Yeah, for writing that out. Yeah, so it's not clear that they agree on the planar part. It's also not clear the cycles. I've got obviously a lot of 4 cycles here. Squares and rectangles and stuff. But over here, I bet you could do that too. You like start at A and go to H and go to B and go to G and go back to A and do another bow tie. Right, there's lots of those in there. Not just the existence of these cycles, but the numbers of them. If one of the graphs has 17 4 cycles and the other one has 16 4 cycles, they wouldn't be isomorphic. Yeah. But these graphs seem to be agreeing pretty nicely for the most part. And it actually turns out that after a while, you get a little bit convinced that maybe they are isomorphic. And in fact, that is the case. So let me try and give you the theta, because I said before, if the graphs are isomorphic, we have to be able to produce an isomorphism. So this means we have to write down, theta of everything and see if we can see if we agree with it. So we would be plugging in, A, B, C, D, right? And then E, F, G, and H. We have to evaluate all of these. We have to make a bijection here. We would have to create this bijection. And this would have to be an edge preserving bijection. And because all of the vertices have the same degree and there's a lot of symmetry to the graph, when the graph is pretty much symmetric, you can kind of start wherever you want to start. So I could just decide to start off by associating the A with the number 1. Okay, now here's the thing. The A is associated with the number 1, which means that anything that's connected with A, which would be F, G, and H, has to be assigned to the numbers that are connected to 1, which would be 2, 4, and 5. So F, G, H has to line up with 2, 4, 5. You can kind of figure that much out, right? And it may or may not be clear whether you could just do that haphazard any old way you want or not. But it turns out that what I did was I sent F to 2. Okay, so here's this edge from A to F. And then here's the edge from 1 to 2, like so. Okay, so the blue edge connects to the blue edge. And then I sent G to 5. So here's G right here. So A connects to G as well. And 1 connects to 5 as well. So the blue sort of V shape I have here is matching up with the V shape that I have right here. Okay. And so then the remaining vertex is H. So A connects to H. And the remaining vertex here is 4. So H would have to connect to 4. Okay. So that's at least a reasonable thing to start with. Now I could do something like this. I could say, well, here's the 2 and the 5. What vertices are connected to both of those? Well, 1 was, but there's one other vertex.
A 6.
6, right? 6 is connected to 2 and 5. So I come over here and say, oh, 2 and 5 are connected to 6. Well, what are F and G connected to? So F and G, is there a vertex that both of those are connected to?
D.
D. So there's only one vertex that's connected to both F and G, right, aside from A. And that was D, so D must match up with the one vertex here that's connected to both 2 and 5 other than 1, and so that would be 6, as you can see. And we could play that game again, like I could pick, let's do it one more time. Are you guys following this?
Yeah,
So I could pick 2 and 4. 2 and 4, okay, those are both connected to 1. What's the other vertex that 2 and 4 are both connected to? 3, right?
3, yeah.
Okay, so 2 and 4, let's look at where they got sent from. They came from F and H. So let's look over here at F and H. Other than A, what vertex is connected to both F and H?
C.
C. All right, so C better match up with 3. Like that. And then the last one would be 4 and 5. Okay, the one vertex that 4 and 5 are both connected to would be 8. So I come over here and I ask myself, let's see, 4 and 5 aligns with G and H. So let's go to G and H. What's the vertex that's connected to both G and H other than A? B, right? Oh, so B has to match up to 8. And once you got that figured out, you have process of elimination on your side because it has to be a bijection. So this would have to be 7. Now, I may have made that look like this is somehow unique. That is actually not the case. Once I decided to do 2, 5, and 4 like this, everything else was then forced. There was no more choices to be made. But I wouldn't have had to start off with 2, 4, and 5 here. There's enough of a symmetry here. You could actually have put those in any order that you wanted. It would have had a ripple effect on all of these other vertices. They would have been mapped differently as well. But you sort of make an initial stab at it and then kind of go from there. But what I was saying earlier, guys, is that if this, so this would be a yes, and I would not be expecting you to then take every pair of vertices in both graphs and make sure that the edges are compatible. You could just give me this and leave that as an answer, okay? And then it'll be my job to check your answer. If I find something that's not compatible, I'll let you know, but just writing down the theta should be pretty good. You guys kind of get the idea of this one? So I'm really sorry, I forgot to bring, somehow, it's in my office, I swear. I forgot to bring the group work I wanted to do, but what I think I'm gonna do is have you try to do this group work anyway, if I can make this a little bit. Well, can you guys see these graphs okay? If I've set you around, we can't use this board though, if I leave the screen down. How about we try and make this work? There are 3 more of these. Anybody who thinks this is too easy, you can start with part C. And try these out, but see if you can grab 2 or 3 people and draw these graphs out in your groups and try to decide whether they're isomorphic or not. And I'll come give you a hand, okay? Yeah, you can also take a picture with your phone. That way you can just have it right in front of you there. And why don't you guys come on up and let's see what you can do with these 3 problems. This is from group work number 9. I'll come around.
We can work them together. So let's see, A, B, C. A, B, C. Okay, so D. Yes. We can go somewhere.
Should be plenty of room. Yeah, you guys can steal this space. Yeah, I'm stealing your normal board. Somehow, you guys have to let those papers.
Maybe I'll do it.
I guess that happens. Yeah, if you need to take a picture of those graphs, just so you have them to play with. I labeled them for you, so you don't have to do that part.
Oh, yeah, I know.
Is there traffic bad?
It's so bad.
You know, somebody in my morning class said the same thing. What's going on?
because we're just going there. I don't know.
Okay, I don't know if it's to the Dodgers game.
Yeah, but you know,
People got drunk last night and got in an accident and everything.
I was in that day, there was so much
Which is crazy, they don't even have a day off.
And my mom and dad was like, it's still on, it's still on.
That's amazing.
Shower, like, it was like 11, I was like, get ready with my it's trying to come out, it's still on. Oh, honey, okay, goodbye. We'll be fine. And then the chocolate today. Oh.
You guys are gonna get all of this right, I suppose. So I'll let you guys be on the board. And this will be all over the internet, so. It's all good.
Oh. Oh, yeah. So you already counted the edges? Nine, yeah. Later. I mean, they are. Oh, the degree. Oh, okay. This one's 4.
Yeah.
1, 2, 3, 4. 5.
So if you feel confident.
So the highest one on this graph,
Just figure that one out.
oh, and then we have,
Oh, this one has at least a degree of 3, but then it's 3. So you don't even do the whole thing.
I was just writing it. So
Oh, you
this
guys
one-
got A done
Yeah,
immediately.
this one doesn't have any.
Beautiful.
Triangles here. Any, I don't think we have any. It is. Yeah. I don't think. Oh, yeah, there's a.
Oh, you just, we have 1, 2, 3 here, and there's not any no.
Oh, yeah.
I'm like, was it that last section?
I think those are.
Actually, no, this one's gonna be, none of these are 3 yet. It's
What are we coming up?
not.
Oh, you're already done with part eight? What was the conclusion there? They're not isomorphic?
3, yeah, 3 cycles, they have 2 cycles, and then none.
This has only 2 3 cycles, are you sure?
So it has at least 1.
It has at least 2. I can see the triangle here and the triangle here. I just want to make sure there's nothing else. You're right. This one has none. You know, a clever way to figure that out is if you start by putting like a circle around one of the vertices, and then anything connected to that circle, you could put a diamond around. So you can do something like this, and then anything connected back to a diamond becomes a circle again. And you can see that, so now none of the circles are connected and none of the diamonds are connected. And the point being that for a 3 cycle, if you actually had a triangle in this graph, then, you'd have to have, a circle. You'd either have to have 2 diamonds connected or you'd have to have 2 circles connected. So this is kind of an interesting way to reason it out. We're going to talk about bipartite graphs soon, and this related to this idea. But you're absolutely right. This cannot have any 3 cycles. And this one clearly does. So. Good, I'm happy. Now, you want the challenge problem? Tripartite. Which will take a while just to draw it.
All right, so the edges not done? Yeah. Vertex, there's 6, the degree of sequence, that's where.
We all have degree 3.
They all have degree 3.
That's what I did.
1, 2, 3. Triangle here, 3 seconds on this guy, but there's no 2 seconds on this one.
Oh, yeah.
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 And then, yeah.
It's actually not. For the second one, yes, that's right, so. It looks like there's a lot of recycling.
So it looks like this,
Real
it's basically a
point is,
rectangle, you repeat it the same way. So this kind of like 1, 2, 3, 4. This cycle is the same as going into.
If you.
As a rectangle.
Anything
That makes sense.
And then anything connected to a diamond, I can draw a circle. And on this graph, what happens is you see that any edge is always.
Yeah, but, right, you have the loop 1, 2, 3, 4, not loop, but cycle. Yeah, that's.
It's that same.
So whether it's
Start with circle
entire
and make a
rectangle.
diamond, you have to make this a diamond as well, and your course, right?
And we gotta put one cycle here, so it's gonna be A,
So this graph doesn't have,
E,
and so,
C.
I see.
that
Kind of like.
He says like a
There's
twist,
like-
like.
you have to have two.
Kind of like easy.
Yeah.
Be a switch.
It's kind of another way. It's called-
Exactly.
Yeah, which is the same.
But that was what the, yeah, it's a cool, it's a cool piece of paper. So
Okay,
if you
you're
wanna
looking for the
cool it,
challenge problem.
so
Yes, right.
the 2 and 3.
You know how to do it?
No,
Let them
Yeah, cause it's.
help lead them to the. You can give them a hint.
This wild act.
Yeah, that's cool, that's cool, that's cool. Okay, and how are we all feeling? You guys doing well?
Parking.
It's on that one for sure. This one you're getting some. Okay, sounds good, sounds good. Sounds good. What
Alright,
do we got?
we got. Oh, no.
No and no, all right. I like
It doesn't necessarily have to be planar, they just have to.
the three cycle
both be
issue.
planar.
Yes, right. This graph does not have a three cycle. I agree.
I feel like
Okay.
one of them does.
And the other one does, yeah, I like it. Okay. Now you gotta try to draw, just drawing parts.
Yeah, I'm gonna.
You got your little.
Every
graph.
every vertex is connected
All right.
by.
Nice of you to do the drawing.
And like they cycle in the way that's like drawn.
I mean,
They're connected to the.
And then this one is the same thing, it's just different.
Yeah.
They're connected to these four, and this one. Literally from one.
Right. Okay, that's a good idea. Okay, maybe you can help them get the picture.
Are we working under?
Any ideas? Yeah.
Are we assuming that there's something that makes all these graphs not isomorphic, or can we? The question says find a structural property.
I think that's not the whole question. I think the question, if we scroll them up would say, they might be isomorphic, or they might not be isomorphic. However, I can tell you these graphs are not isomorphic. I'm gonna take the fun out of it.
That's fine.
But they're coming up with the structural differences, what I, which is gonna be the interesting.
So it's not sitting right with me.
I think we're
Yeah.
Because they've all got this outer.
Yeah, you would probably try a few of the properties, and they all seem compatible.
Maybe safeguard or something. And they just work on that.
Then you're doing good.
And if I don't, see if there's a way.
It can be a little bit of an open-ended issue, and I don't have like, I wish I had like
Alright, so look
a
at one.
magic pill. that would
It's
solve
not
the problem.
connected to anything.
Yeah.
Yeah.
You think we can look at what they're connected to? To see
And we're talking about an hour and 15 minutes.
So, like,
Probably
okay.
not gonna go too hog
So I think
wild.
the four-
I would say part C here.
four is gonna be not connected to
Most challenging.
107, and 6 is gonna be not connected to 1 and 2.
I got you,
Right?
I got you.
So.
Your whole group is abandoned.
How do I put
They're all
them right there? Six.
Yeah. Okay.
Someone's gonna draw it.
So that's like what they're not connected to, and then we can see if it's different over here, then they'll have different cycles, I think.
This one's not connected to B, it's not connected to C, connected to D, connected to E, connected to G, and C. And this is the same. Connected
Just
to
even
D.
drawing the graph, right?
It's not connected.
Kind of half the battle, yeah, right.
Also DNA?
Let's try to.
Just draw them like some.
He said they're all not.
Oh, they're all not?
Yeah. That's what. So the ones that are not connected here share the next ones that are not connected to, but these ones no.
It would be a little tough, yeah, it might be a little
But
tough.
the issue is that I don't think
It's a
the
little bit of a challenging one. Once you figure out
labeling doesn't
the
matter.
secret to it, it's like, oh, that's really not
Yeah.
bad. Yeah, I'm gonna let you guys suffer for a
Yeah.
couple minutes thinking of it, and then I.
Okay.
Yeah.
I mean, that definitely
I know
means
you
that
guys
there's
are
a,
good hands.
there's a connection here that
Okay.
isn't a connection.
Okay.
What if you label it?
What if you map one gene? Solid. The relationships.
It would share that.
Right.
Like,
I'll give you a hint, looking for cycles.
but the issue is that like we could make it out, since you said they're not isomorphic, like we could make an isomorphism that fix somewhere, but that doesn't necessarily. prove that it's made of that.
Oh, wait, you. Guys, looking for cycles and looking for relationships between vertices is gonna be a little bit of a fool's errand on this one. It's gonna be a little bit tricky.
All we've got so far is that every point has 2 points it's not connected to,
Uh-huh.
but the 2 points that these ones are connected to,
Uh-huh.
or one of them is different. Like they'll have this one's not connected to 3, and this one's not connected to 7. These ones over here, A isn't connected to G and C, but then G and C are both.
Can I make a suggestion based on what you're saying? Because you are totally on the right track.
Let's see.
Can we redraw 2 graphs that show me the non-edges?
Okay,
So this is called the complement graph. So if we take out all of these edges and we draw the edges that are actually not here, let's see what we get. And let's take this graph, let's take all of these edges that are not here and then compare those. Because if they're graphs are isomorphic, then non-edges preserve just as much as the edges do.
So they're all.
Yeah, that's gonna be a nice idea. Give it a try. Maybe what you could do is just keep the graphs that you have and maybe like take maybe a black marker and put it on top of this one. You'll need maybe like a red marker over there and draw the non-edges in and see what kind of a shape you get.
No, you said draw the. All the edges.
Because each one does, this doesn't select the 2 other ones, so it'd probably be cleaner to draw. Because we just have to compare the components. We don't necessarily.
I know, I think so. Oh, yeah, E is not connected.
Whoa.
No, that's not much connected. He's saying, we want to connect the ones that are not.
How about from,
We're listing them. These are the ones that are not connected. So B is not connected to B. G is not connected to B. Oh, okay, so that's what we're looking for. We can't do the data thing. This is not isomorphic. You could, I was just trying to not. Oh, it's a square? Oh, that's fair. Yeah, we just put like that one. I just think of it as like rotating. If you start at A, it'll be G and C. If you go to E, it'll be H and D. Right? And this it should be G.
if you drew in the dominant.
Can I beat eight?
And you drew in the
B
to this guy. If these were isomorphic, those.
So then like full triangle.
Those Van graphs.
B and E.
Graphs. So instead of analyzing these, let's analyze.
Everything should, I think everything should finally have two there.
Or I would use it.
A and B are.
You could take this blue marker and you could say. Draw the.
So you see what's succeeding? And C will be A and E.
Just an idea, but you might.
I'm pretty sure.
It's like a start.
And C will be A and E.
Oh, like you said.
So D will be G
Oh, there's
and
another.
B. Then we're-
Okay.
so negative-
Anybody need a hand?
No.
My life just stopped.
Oh, it's not so much.
So you just need to each word next to something.
Yeah.
Did you hear me say that again? Nice. Well, good thing that I submitted that.
The B's are one more, it's not number two now.
We have two.
We have eight squared.
Oh, yeah.
So that's-
How many non-ends we have?
Yeah.
Those graphs being isomorphic, or those graphs not being isomorphic would mean that these are.
Just one of these. Oh, it. Oh.
So you have to see what you have done.
Hear me now?
B and H and D.
On this one, yeah.
But I think that's A. That just.
Right, that is exactly the idea. This one,
Yeah.
this one, well, it's not just that. Yeah, but the issue is that you're gonna have off kilter squares. I can kind
Like,
of.
I'm sorry, G and C.
And this one.
Yeah, G and C.
One giant thing. I had thought.
Yeah,
You
you
can see. This is not connected. This is like 4 points in a square and then 4 different points in an unconnected.
So there is the same.
I can't.
That's what. We were listing them.
So they're the same, the complement should be the same.
That was like.
Oh.
They've all got two.
But if you see the number of courses, this was not the
Yeah,
same,
I think that's
then
it.
the number of edges.
Oh.
I think.
Because you have 8 in the graph, so the total of the edges of the.
I could
Yeah, but they're like weird triangles.
No,
They're
they're
not
like,
quite.
well, the number
Okay,
of
I wanna
edges
try and hit
is
star
not
and-
different.
Circle and diamond.
Oh,
Yeah.
but when you add them together, it adds up to n. And so this is H2.
Yeah.
Oh, yeah, there's no way back.
If you said that one of the graphs had 8 inches, then that would mean that the original graphs had 18 inches versus 16. So you would have, they wouldn't have agreed in the first.
Worry about this idea.
That's right, you wouldn't have to-
Be obvious.
It'd be obvious. Yeah, that's exactly right.
That's right.
Did you guys get that to work?
The complement graphs have different amount of cycles.
Yes, you have two. Actually, they're not even, the one on the left is not even connected.
Right.
Whereas this thing on the right is connected. So that's a difference between the complement graphs that therefore means the original graphs are not isomorphic. Isn't that clever? I love that. I love that.
Two non-connected graphs.
You guys get any idea back there?
Stop, I'm done.
You did.
Just redraw it. I mean, like, you got two
Two
different.
squares that are like not connected.
So-
So guys, it's a.
Well.
You said this is really great to go into he's doing it.
Graphs are all.
I told him, I said that. Because I said, if you wanna provide some more systems.
You have to show- I feel like
it's just for you to feel confident that it's.
If you do it on a computer, you can actually.
Oh, yeah.
Yeah, and you're spending a little time.
So
There's
definitely.
I'm probably doing some special lab. I'm probably doing all the. stuff.
I would not have.
Right, on my own. Yeah, no.
look at it.
I always get scared when I like, it's certain confidence and stuff, I'm like, oh, I don't need that, like, yeah, give that. And I actually took a while to think about that, like, I kept on thinking.
Dude, I did enough of that in here that I was like, I'm not matching it, so I think something else. And I was making so many mistakes in the three-way intersection, I'm like, ah, because the time was like 5 minutes, I was like, ah. If there wasn't a time.
Good job, good job. You guys figured it out? Yes, that looks great. That looks great. Hey, it looks like everybody's figuring this out pretty much. Did you guys get this to work out? Yes, the G prime has a single big 8 site.
Yeah.
Whereas the other one actually has 2 disconnected squares. of 4 segments. That's it. Good job. All right. Yeah, we can erase, if you're good. I appreciate that. Somebody's got really nice handwriting.
That's the teacher.
Oh, okay, yeah. Yeah, that's good handwriting, let me tell you. All right, guys, great job on that. I think we got most of the way through that. There's a couple of other problems on that group work, but we'll let those go. Good job, guys.
Right, remember how we have the there?
Okay.
They were connected. And then that thing was okay, we're And here we go. Sorry.
So excited we're doing graph theory now. I love graph theory. So much fun. Use the eraser to draw the edges.
Alright, name.
Okay, guys, I've only got about 8 minutes here, so I'm gonna, I'll let them keep talking. I'm just gonna start. I only got a few minutes. I do want to get started on this next idea because it's a pretty simple one. We can easily knock this out. The next section here, we're kind of diving in now into the deeper part of chapter 11, which is 11.2. And this is going to be a new concept that I just want to get our feet wet with today. Something called Eulerian trails in a graph. So this could be another structural difference. So if one graph has an Eulerian trail and the other one doesn't, well, then they're not isomorphic. So you could use that. Let me just recall what the definition of a trail is. We mentioned it last Thursday, but I just want to make sure we're all on the same page. So a trail in a graph is a walk. It is a walk with no repeated edges. So you're just walking along the edges of the graph and you're just not repeating any edges, okay? So we could just imagine trying to find trails in a graph. So I'm just gonna draw a quick picture here. The specifics of this picture is not that critical, so I'm not gonna worry about this too much, but we can kind of just draw something. Maybe something like that is good enough for my purposes. Don't worry if you don't have it exactly drawn like that. But we could, you know, have a picture like this and we could think about taking a walk in this graph. And better than that, we can think about taking a trail in this graph. In other words, could we take a walk and not go across the same edge twice? Well, that you obviously can do because you can just take a short walk from, you know, from A to B. That, and you can just use one edge. You're not repeating any edges if you do that. So this gets more interesting though. I'm gonna just go ahead and label all these vertices. This gets more interesting if I ask you to take a trail in this graph that actually uses every edge. Remember, we're not allowed to use an edge more than once. But what if I said I do want to use every edge? So that would be every edge exactly once. So that is the definition that I would like to put here. And then it may not be obvious just looking at it right away, whether you would have such a trail in this graph or not. So a trail in a general graph, notice I did put loops in this example that I have. So we can talk about this for a general graph, which includes multi-edges and loops and so on. That uses, so a trail that uses every edge. This is the key, every edge. A trail that uses every edge is called an Eulerian trail. Named, of course, after Euler. And this is a fairly famous type of problem that I give you a graph and I ask you, does it have an Eulerian trail? Can I wander around and hit every edge exactly once? Remember, you have to hit every edge, but you can't hit it more than once. So you're hitting every edge exactly once to do that. Obviously, I'll make a remark here, just kind of just to get the wheels turning about thinking about this. In order to have an Eulerian trail, your graph would have to be connected to begin with. If you had two disconnected parts, remember you're taking a walk. So the walk, if you had something like this, which is what happened on the group work, you can't, use every edge on a walk because you would be forced to jump across from one square to the other in order to accomplish that. And you're not allowed to do that. You have to stay on the edges that are in the graph. So I'll just add that as a remark here. Eulerian trails can only exist in connected graphs. Not going to happen otherwise, right? So it has to be only in connected graphs. And of course, this Eulerian trail could be open or closed. So remember, a closed trail is one that finishes back at the same place that it started. So you take a walk through the graph, you hit every edge and end up back where you started. This would be, if you were out on a national parks road trip trying to see as much scenery as possible. You never wanted to go down the same highway twice, but you did want to get to every single highway that was there and then finally get back home to where you started. That would be trying to find a closed Eulerian trail out of the highways that connect those parks together. So let's just maybe throw an example up here. Actually, it turns out the decision whether a graph has an Eulerian trail or not is actually very easy. It's an easy condition. So it may not seem easy at this moment, but it's actually very easy. Whether I'll do it in 3 minutes or not, I don't know, but I can always get you to come back on Thursday for the answer. But let's just draw one example here. So does this graph, I'll just draw it in a second. Does this graph have a closed Eulerian trail? So this is going to be a closed route that uses every edge exactly once. So here's my picture. I'm going to put a vertex A connected on the right to a vertex B. And then I'm going to form out a triangle out of that. So B, C, and D makes a triangle here. And then I'm going to have two more vertices over here, which are E and F. And I'm going to make a connection from C to E and from D to F. And then I'm going to do the diagonal connections as well like that. So there's my graph. This label here. So there's the graph. And the question is going to be, does it have a closed Eulerian trail? What do you guys think? Mason, why not? Okay, there's a vertex. Well, actually, this is an odd vertex, and so is this.
Then it does.
It does? A closed Eulerian trail? So you have to, so here's the problem. you have to use every edge. You have to get back to where you started. And you have a vertex over here. Is this what you're gonna say?
Yeah, because you can only come to A, but you can't leave, or if you leave, you can.
Yeah, if you started at A, okay, if you started at A, you could use this edge to leave, but you can never get back to A. Right? So this is an important observation. You have to be able to enter and then leave every vertex, right? If it's gonna be closed, right? So this is gonna be no, if you wanna give a little reason for yourself, I would just give the simple reason that the degree of A is equal to just 1. If you have any vertex of degree 1, you're not gonna be able to both enter and leave that vertex, which is going to be problematic. So is that a hand? Yes.
Just a comment.
Yeah.
That would be called a bridge, right?
Yeah, we're gonna get to that a little bit later. A bridge is just an edge that when you remove it, it disconnects your graph. And that would be true here, exactly. So that's a bridge, but the point being that you cannot enter and leave that vertex. So does anybody think they might know, I'm running out of time here, but does anybody think they might know what would be the condition to have a closed Eulerian trail? I'll state it for you here. First of all, I'm going to assume that G is connected because I've already made the comment that if the graph is not connected, we can't have an Eulerian trail. So let's assume that G is, let's let G be a connected general graph. Then it turns out that we have a very easy condition. Then G has a closed Eulerian trail if and only if. I'm wondering if people have an idea. Marcus, you wanna try it?
Is it if, the degree of every vertex has to be at least 2?
The degree of every vertex has to be at least 2 is close. It has to do with degrees of vertices. Mason?
And they either all have to be odd or all have to be even or 2 have to be odd.
Actually, none of them can be odd for a closed Eulerian trail. You guys together pretty much sorted it out. It's that every vertex has to have even degree. It's just that simple. So the degree, if and only if the degree of V is even for all vertices. I will write down on Thursday a formal proof of this, but just so you have the idea, I can explain it super easy, just in words since we're out of time. The idea is just that in order to actually use every edge and not get stuck somewhere, being forced to reuse an edge, you have to be able to enter and then leave every vertex. Entering requires a degree and leaving requires another degree. That's 2, degree of 2. And you could go back to that vertex again, but that would require 2 more edges that you haven't used so far. So in that case, the degree would be 4 or 6 or 8 or 12. Every vertex has to have even degree. So this is an easy one to check. That's the nice thing about it. On Thursday, I will prove this and we'll use this to actually create these closed Eulerian trails. This is a very high application topic, so something I definitely want to spend a little more time on. Thanks, guys, for today. Appreciate you being here, and I hope you have a good rest of your day. I'll be downstairs if anybody wants to talk about homework or anything else. Feel free to drop by. I always love talking to you guys. Have a wonderful rest of your day.